Okay, welcome to CET 466 Halloween edition. I liked the meme with pumpkins and various logic representations. So trick or treat, and then trick and treat in a minute behind the morning.
Is the
Trick exclusive or treat? Right, you can either. And that's interesting, right? So the language, the idea of trick or treat is usually either you get tricked or you get a treat, which is this one, right? It's not, you can get both, which is kind of interesting. And then here's trick negative exclusive or XNOR, right? So it's only the in between and everything outside it. And trick NAND treat, so if it's both of them, that doesn't happen. And trick non-treat, you don't get either. So I thought it was fun. Just a reminder about the textbook, and that's where we are, right? So should try and finish up lab 7, the counter today, and hopefully kick off lab 8, which hopefully we'll finish next week. I do want to talk about the group project today. We're not going to start the group project for another couple of weeks, so how much we get done, we'll see. But I have rather than getting everybody all grouped in pairs to do a complex thing, I think what we'll do is we'll choose one of the projects, and I've chosen one, and we'll get teams of people to work on specific parts of that, and then we'll try and glue it all together. And what that might mean is we might have to have a team that is the glue team, right? I call them the system integration team, the ones that have to pull everything together. But we'll talk about that later. Here's a list of stuff, and most of that we've talked about. I still need to talk about the library functions, which is why that's highlighted. There's the accessible items. I didn't get a releaser the Zybook stuff early enough today, this week, so that's all due starting next week. It's a bit longer than normal, so because I only released it yesterday. So far I have had 10 people take the midterm, and 2 I've got booked for various scheduling reasons. I think the one person who was no booking has actually booked, but I had stopped the oral exam booking part of my bookings page, and they've booked just using the general consultation, so we'll see how that goes. So the project that I'm thinking we should do is build a CPU. And the idea will be that, and I'll talk about the architecture in a bit, the idea will be that each group gets to do a piece of the architecture. And there's various other things that aren't really VHDL that we've got to decide on. What's the instruction set, right? What does what peripherals are we talking about? How do we get stuff into it? How do we get stuff out of it? But that's all manageable. So that's what I want to get through today. Look at that CPU, and I'm not going to go into detail about it today. I just want to go do a quick run through, and then we'll dive into it more deeply next week. I do want to look at the Zybook chapters 1 and 2. And just to see the connection, because one of the things with this course compared to 363 is, as I hope you saw with the 4-bit adder example, right, is you've got to change your mindset about how you think about logic. You can't just go with gates. You still need to understand Boolean logic. You still need to understand, okay, you actually do have to implement this as a gate in effect, and things like propagation delay and fan out and all of that stuff still needs to be thought of. But a lot of that, when you move to VHDL, is taken care of for you to some extent by the compiler, right? Because it does a lot of that stuff. But anyway, I want to build up by looking at the introductory chapters in the Xi book, and then we'll, in a couple of weeks' time, we'll move on towards the VHDL pieces. So what I wanted to do is switch. So I didn't do it, and maybe I should have, but there's a really nice series of lectures, and there's a textbook by these guys, Noguson and Shimon Shopping. Shimon has been very kind and given me access to all the professor material behind this stuff, so it's quite good. Right, and this is a roadmap, if you like, of how they've looked at it. And we will probably have to do some of this prep material, right? Or at least some people in the class will have to look at the prep material, writing the low-level program. But we can do that. So what they've done is they start off with, right, the machine language. What is this CPU going to do? What can you tell the CPU to do? And you might need to be able to load. So you load from a memory location into a register on the CPU. You may want to move from a register to a memory location. Right? So that's one thing. You may also want to do simple stuff like add or subtract or multiply you need to do. But the first piece up there in the top left is to understand what the CPU is going to do. Right? And then we can talk about, well, how do we do that? How do we make a hardware platform that does that? And the top level abstraction, if you like, is just the computer. Right? Maybe you think about a big chip, Intel or AMD chip that you want to do, but then inside that chip, there's various other pieces. There's an ALU, an arithmetic logic unit, right? If you're doing an add, then that's probably going to be done in the ALU. if you're doing a load, that's probably going to be going between the RAM and the registers, if there's any distinction between those two things. And then below that, right, there's the actual elementary gates that are actually going to do it. And we should already know about that stuff. But in this particular textbook, that's from the introductory chapters, chapter 1 through chapter 3. Like I said, I'm only going to really skim through this. Right, so no, it don't know why it does that. So here's a little bit more of a deeper dive into what we might think of as the pieces of the computer. Right, there's the RAM. Right, that's the memory. What do you use the memory for? And get my Picking on Students app open. Where I put it? Michael, what do you use the memory for?
Regular computer.
On it? Any computer?
Writing applications.
Writing applications.
Not
So
writing
the program, right? That's one thing, right? Eric, what else do you use the memory?
Assigning addresses to registers.
Yeah, we'd have to think about that, but yes, you probably also need to store what the computer is currently working on in the register, and that needs some sort of a memory. Anas, what else?
The memory.
The memory, yeah. What else?
Well, it's used to load the programs that are running on the computer now, and it doesn't save what's on there. So once the power is off, everything's deleted. So, and pretty much, I think that should be the answer.
Okay. So
Like it's not continuity, non-continuity, right?
right. So that's actually a sort of separate issue, but it is something, right? There's the issue of volatile versus non-volatile. Right. So, and then the other thing I would actually put up here is, for me, registers are immediate data. It's data that you need right now. Right? But you might want to store data as well. So I would also add data to what you're going to use the memory for. Right. Okay, so that's the RAM, and the nice thing about this particular thing is you've got a few things. You've got all of the I/O, right? You've got a load input, an in input, and an address input, and then you've got one output, which is the information coming out. Okay, and similarly, so here they've pulled the registers out a little bit separately, right? And the reason the register is going to be a little bit separate from the RAM is RAM is going to be much bigger, there's much more of it, and the other thing is the register has got to be much more closely associated with the ALU, with what's happening inside the computer right now. And then the ALU, right, the arithmetic logic unit, has 1, 2 inputs, 3 inputs, and that F input up there is basically saying what function is going to happen now, right? So what instruction is going to be executed right now. So based on what's happening on input X and input Y, what happens inside the ALU is determined by that input X. Okay. And then the other thing down here, any idea what that is?
Program counter.
Program counter. Very good. Right. So the ALU just does particular functions, right? So I was hoping somebody would say personal computer, but the down at this level, we've got to figure out what the next step is, or what the current step is. So you can see that there's a similarity between. Now I'm a little confused, because I would have thought that the program counter will tell you what the next address is. So we might have to figure out, because it looks like the program counter is more like the width of the memory locations, rather than the width of the address of the memory location. So we might have to think about that.
Do the numbers represent the bus?
Yeah, so this that's right. So this way of doing things, right? You've got a line, and you've got a slash, and then you've got a number. That line is indicating that there are n separate wires, or bits, or whatever you want to call it. Right. So here there's 16. 16, 16. The only different one is 14, so I might have to read up about that. And then where there's no indication of a number, right, load and load increment reset, that's just a single wire. Okay. Okay, and we're going to have to, this is apparently a a simple program written in their machine code. So we might have to figure out what's happening there. It looks like it's defining a variable, I, set that variable to 1, then defining another variable, sum, and set that variable to 0. And I'm not sure what's happening here. Right, I think what's supposed to happen is it's supposed to increment I and add I to sum. But I can't quite see that happening here. Yeah, I'm going to have to read up on the machine language, so let me make a note of that so we can figure out how that works. And maybe that's something I'll take on as part of getting this to okay, so so the idea would be that we need to have one group that do the RAM, maybe a couple of groups look at the ALU, one group do the program counter, and one group do the registers. And I think you can, I hope anyway, you can already start thinking about, right, this port is going to have a stated logic vector 16 down to 0 or 15 down to 0, just a stated logic input load, and here again we've got a stated logic vector 15 down to 0 coming down. I didn't talk about it, but that there that exists on most of these, I didn't see it here. That's the clock input, right? So it's an implied clock input. As you're aware, one of the big selling points of a lot of CPUs these days is the clock rate, right? It's a 4 gigahertz or a 6 gigahertz clock. So we need to think about that. Our clock rate on the boards is only, I think, maximum of 50 megahertz. So it's going to be a little slow, at least compared to these things. Now, was there one other thing I wanted to talk about? Okay, so here's a slightly different version, right? So, and this is talking more about what I said earlier, right? How are we going to do the I/O? Right, where does the input come from? And remember, we've only got a couple of buttons on the input. And where does the output go to? Does do we just use the LEDs? Do we use the 7-segment displays? How do we do the output? So that's something I suggest you think about, because once we've built it, it'd be nice to program it to do something. And I think the only thing we can hope to have it do is a hello world type program. But what does that mean, right? We don't have a device that shows text. So what does that mean? Does it mean that we've got a buzzer there? Does it output hello world in Morse code on the buzzer, what does it do? Okay. So that's actually something else I'll have a think about. And right, so that's just the pieces. The fetch execute cycle, right? That program counter points to a particular part of memory, and what's got to happen is it's got to go to that memory, take the data out of it, and present it as the f function of the ALU, right? And then that f function tells other parts to maybe pull in to the x input or the y input or both and do something to the output. And the rest is, I'll talk more about this next week. I want to try and get Lab 7 and Lab 8, Lab 7 finished and Lab 8 started today. Any questions about what I've talked about with the project? Does that sound like something that would be good? Yeah? I think it'd be fun. It's going to take a little bit to get organised and figure out where the partitions are. As I said, I think I'm going to need a couple of people to act as the glue. Yeah, Mike?
Can we just scrap Lab 7 and 8 and start this? We just scrap it. This does sound fun.
I could certainly scrap Lab 8. I would like to get Lab 7 done. Okay? So, is that? I'm happy to. I would like. I haven't done this before, so I'm not sure how long it's going to take. But if I would like to get it done, so if scrapping Lab 8 gets it done, yeah. What? Any? I'll take that as a positive thing. Okay. These notes are available up in OneNote, so have a read through them. Okay. So I want to go back there. And so I do want to talk about, quickly look at Chapter 1. I do have that printed out, but I think it might be better to look at it on the website. Just because I think the animation is pretty good to see.
Can you just make an official statement?
Testing. Yes, we will cancel Lab 8 and do the Manta Tetris project. You okay with that now?
Perfect.
It's going live to YouTube, in public YouTube, so you've got a recording anyway. So
but you can cut that part out.
Right. Now I have got the proof now.
Okay. Let's. I don't know what's wrong with my computer today, but it's just taking forever to load anything, and then because I double click on it, it tries to load the same thing twice.
Can't you swindle the school into getting the new one?
Yeah, I probably should.
$80 million in donations.
So what? Last semester, while it was online, I didn't have a webcam at home, so the school was offering webcams, so I got a webcam. It was okay. It was cheap and cheerful. That worked fine. And then
right at the end of the semester, they sent me an email, you must bring this back. And I was still teaching over the summer, so I said, "Oh, give me a..." And then I got my act together and I bought myself a nicer one. So, but yeah, there. And then I stopped reading the emails from the IT department that come out periodically, because just about everything says, the first thing is about CCSU equipment and being careful with it and bringing it, if you bring it home. And yes, that's okay, just get me to sign in blood when I get it, and then I'm done. So you don't have to remind me every week or whatever it is.
The federal government was going for.
Yeah, I don't know. I think I'd almost prefer the federal government sometimes. Sign in. Oh. I usually access this on my desktop computer, so that's why. Now, do we have... No? Why did it? I don't want to do that. Okay, so let's go back to basics, right? So you should have learned about in CET 236 or something similar, or physics, about Ohm's law, voltage and current and resistance. And what we've done so far in 466 is we've forgotten all about that, right? We're just looking at ones and zeros. But the trouble is we can't forget about those things, right? Just because we conceptualize what's happening in our FPGA as ones and zeros doesn't mean there isn't a voltage, there isn't a current. There is, right? Does anybody remember what the active high voltage on the FPGA is?
3.3.
I don't believe so.
So 7.
7? No. Muhammad, any?
2.2.
2.2? Closer.
1.5.
1 volt.
Closer still.
0.3.
I'm not going to... Let me just see if I can fire it up here, because it'll take too long to fire up on my laptop. Maybe it'll take too long to fire up here too. So this isn't going out on the recording. But all I'm going to do is I'm going to go and look at the devices. Maybe? I think I've
told you before, I've never had a computer that's fast enough for me.
These computers are 10 years old, so the laptop might be better.
Yeah. Optiplex 1920. Surprised, it's usually started up like that.
It usually crashes.
I think you have to close it. If you just double tap, it'll crash. And then it's not working. Let's restart it.
Oh, that's a feature. Makes it worse.
Thank you. I don't know what that's about.
Says something related to
So, I don't know whether you can see it, you may not be able to see it, but that's the C8 we're using, and the core voltage is 1.2 volts. Okay. So, I think the peripherals are all 3.3 volts, but I think the core of the FPGA is running at a much lower voltage. Okay, so don't forget that you're still running on a voltage, on a current with a resistance. So when I was an undergrad and I had an internship, I worked in the claims department of a PC manufacturer in Australia. And we would get all the warranty claims coming in and have to say what had happened to it and fix it if we could. And back then, it wasn't necessarily known that electronics could be affected by static electricity. And unfortunately, that PC manufacturer's manufacturing manager didn't believe it. So they had very few anti-static precautions in manufacturing. So we would get a lot of warranty claims that were static damage at manufacture. Right? They didn't necessarily show up in the tests because the manufacturing manager didn't believe it, and so they didn't necessarily do the right tests to test the static damage. So static electricity, just probably, this is probably okay, but this stuff maybe not, right? That can give you a nice charge, or you're probably aware of touching a car's handle or whatever and getting a zap. That can kill electronics. So don't forget about it. And I realise this stuff is stupidly simple, but sometimes stupidly simple, I find, tells you something. Particularly if you've just looked at something more complicated and you come back to the simplicity of a light bulb. Right? In this case, they changed the voltage from 3 volts to 6 volts. So now the thing is, with the logic we're dealing with, whether it's 1.2 or 3.3 or 5 or 7 or whatever the voltage is, doesn't really matter provided you agree on what that voltage is. Right? If you try and connect up a 5 volt output to a 3.3 volt input, that's not going to work. you'll probably blow up the 3.3 volt.
Does the amperage depend on the load?
Sorry, does the
Does the amperage depends on the load? So for example, say we have 6 volts, but we connect 2 different loads to it, and one draws more than the other. Would I guess the amperage be the same for both devices, or?
well, it's going to depend. It's going to depend on the resistance of each device, or the impedance of each device. Right? So you have to then go back to right. So I let's go back to can I go there? There we go. So let's go back here. And let's go to the top. Right, so the yada yada yada. Maybe. So you asked an interesting question, right? Does the connecting other stuff up affect things? And it sort of does, right? So if you just have if you just have a battery, right? And say it's a 12 volt battery, and you connect that up to a bulb, and I'm just going to draw the bulb as a resistor with a glass tube around it, right? And then you connect up another bulb, right? Assuming that they both have the same resistance, right? R1 and R2, and assuming R1 equals R2, then they're both going to have the same current flow through. And if all of this were true, that would happen. You would get the same current in bulb 1 as bulb 2. The trouble is, this is a little theoretical. Now we can still be theoretical, but we can be a bit more realistic. And by a bit more realistic, we can think about the thing that's providing the 12 volts. In reality, the thing that's providing the 12 volts can be modeled like that. Anybody remember that? Right? So this is a 12 volt battery, right? Let's write 12 volts. But in 236 or 233, you learn that you can talk about what's called Thevenin Equivalents. And in reality, a battery is never just 12 volts. A power supply is never just 12 volts. Closer to reality is more something like this, where you've got, maybe it's not 12, but you've got the voltage, and then you've got a series resistance. Now think about what happens if you've got this in here, right? You've got, in the first case, forgetting about R2 for now, in the first case, you've got, let's just go there, right? Let's just forget about everything to the right of that line. In the first case, you've got whatever the current is. But if we're modelling using this, then there's a little bit of a voltage drop. across RTH. RTH is usually quite small, it's a small resistance, but there is an appreciable drop. So what you actually see at the bulb is not 12 volts, it's 11.9. Now think about what happens if you add that extra resistor, or that extra bulb. Now you're trying to put twice the current, pull twice the current out of this device. So you're going to get twice the voltage drop, right? Same, well, twice the current through the same resistance, you get twice the voltage drop. So, sorry, that was quite a long tangent to try and answer your question.
No, that's fine. And the reason why I asked is because, so at home I have this device that calls for 5 volts. And this device needed a specific battery, 5-volt battery that would have to, I guess, connect to it. But I didn't have that specific battery, so I just made up 5 volts.
Yeah.
And for some reason the device was getting very, very hot, but it used the same, like I tested the voltage that I made, and it was just 5 volts. So I was just confused if amperage had anything to do with the load.
Only through Ohm's law or something similar, right? I would have thought if you connect the same voltage up as the device is expecting, it shouldn't get hot. So maybe there's something else going on. Okay. Okay. So let's just go back to full screen here and see what we got. Right, I'm not going to go through and do all the participation activities. You've already done them, but I do want you to have that connectivity back to the basics. Right, it's certainly worthwhile having that connectivity. And increasing voltage. So remember, V equals IR, Ohm's law. Increasing voltage. So I equals V on R. So if you increase the voltage, you increase the current. I equals V on R, decreasing the resistance, increases the current. V equals IR, so I equals V on R, so that's a 3. So they should all be pretty straightforward. And again, that's just checking that you understand Ohm's law. So one of the things I've found really bizarre, I've done a lot of mobile application development. And I used to work for a company that would buy me any device I wanted, it provided it was a target of one of our apps. And I've almost never had a problem with these devices. The thing I usually have a problem with So the thing I almost always have a problem with is that. That's a USB cable. No? And I went away a few weekends ago to not quite upstate New York, but not New York City, into New York. And my wife brought all of her electronics and all of her cables, and both of her cables didn't work for charging her electronics. We had enough, but There's not a lot in these, right? And I actually found that, believe it or not, there is a USB protocol for charging, and very few devices implement it. This is a complete tangent. Sorry, I could talk about this. So let me just finish. There is this little device that I bought. That it's basically a voltmeter and an ammeter for USB. But what it does is if you plug it into a USB port, and it's got 2 extra USB ports, and you plug in a USB cable to it, it'll show you what's happening on that USB cable. And it's really good for diagnosing bad cables. The other thing it's really good for is it does that power protocol. And provided the device, I've had devices that appear to be bricked, and I've left them plugged in overnight to try and charge, and they do not charge, just on a normal USB cable. I plug the same cable into this little device, and it does this protocol, and has recharged and has resurrected at least 3 devices that I can control. So, and again, I'm changing topics, but I highly recommend not forgetting about electronics. So this is kind of interesting, right? This is a relay, right? It's a mechanical switch, electrically controlled mechanical switch. And the reason why, when we talk about problems with software, the reason why we call problems with software bugs is because the earliest computers used relays to do their processing. And because they were huge room-sized things, and one of the first problems they had with these room-sized computers that used relays was moths getting into the contacts. So they had to go in and clean up I never used tubes much, but they're kind of cute. They have to work at a much higher voltage than a lot of things. That's why they glow, right? They've got to be heated up to work properly usually. A lot of, particularly jazz musicians who play electric guitar or electric bass, they like to have a vacuum tube amp because it has a warmer sound, a different sound from the electronic one. The electronic ones sometimes these days try to mimic the sound of a vacuum tube amp. That's different. That's just a transistor. Any idea what that's called? It says integrated circuit, but I would call it something else. So Kevin, any thoughts? No? Fahim, any ideas what you'd call this one here? No? Okay. So that particular style of connector, I would call I would call it a ball grid array, right? Because each of these little dots is a little ball, and if you see the way the printed circuit board is laid out, it's got a lot of little circular dots that connect to each one of these. and each on the actual device itself there is a little ball. So it's a ball grid array, BGA. That's different from some of the other ones. There's another similar, if you see the ICs with all the legs on all four sides, that's called the QFP, quad flat pack. And then the other ones are usually the ones with just straight legs. The quad flat packs have splayed out legs like that, so they're surface mount, but the dips are straight for through hole. Okay. So this is a slightly different type of transistor, right? The usual sort of transistor I'm used to is not one of these MOS transistors, right? But it's still got 3 legs, 3 inputs or 3 connections. I'm used to the standard either NPN or PNP device, which if it were here, it would have angles here and here. It wouldn't have a gap, and there'd be an arrow on the bottom one, either pointing out or pointing in, depending on the type of device. But these are what I call field effect transistors, FETs. So you've got a gate and source in a drum, rather than a base, an emitter, and a collector.
Is this the same technology on a motherboard?
Yeah, a lot of devices these days use MOS as the technology rather than standard silicon or the older silicon. Was it metal oxide silicon and then N-type semiconductor or P-type semiconductor? Oh, that's interesting. And you usually refer to it as CMOS because you can have both N and P type in the same package. So it's complementary. Let's keep. Sorry, I should have. I probably should have gone through this earlier, but anyway. Right. So here's a circuit, and we've got one input A, and it's going to both a non-inverting input on this transistor and an inverting input on this transistor. At least I assume that's an inverting input. And we want to know what Y is. So if A is 0, what's Y? Michael Gallagher, any ideas what if A is 0, what's going to pop out at Y? And if you could explain why, that would be good too. Y is going to be 0. So 0 here, you think it, and could you explain how you get that? Okay, so anybody, let me see if somebody else can. Fahim, any thoughts?
I think it's gonna be 0 as because it's going from the negative transistor when A is 0. So Y is gonna go down to 0 and output will be 0.
So A is 0, so how do you get Y connecting down here?
I want to know the transistor is in the negative way and or in the positive way. That's why I choose figure out first.
Right. So I think that's why I'm thinking that this is an inverting input.
Also, the bottom is positive, the top one is negative.
Right. So if this is 0, then this is turned off, right? But if this is 0, this one's turned on, I think. And if this transistor is turned on, it's going to connect Y to 1. Okay, so I think that's why the connection there. Right, so that's another thing about transistors generally. You have two modes of operation. There's the switching mode, which is what we use them for in digital logic. And then there's the amplification mode, which is what you would do if you want to make an audio amplifier or something analog. But we're only usually interested in the digital one in this course. Right, so creating digital circuits to achieve desired digital system behavior. That's basically what this course is about. And it's just explaining the difference between digital, where we've just got the two values, 0 or 1, maybe, and versus analog, where we have a floating point number, right? Minus 0.23 plus 0.672. I get a little cautious around the word digital, because really digital is just about, well, it starts with digits, right? It starts with fingers. But digital can be any number represented on a computer, right? I can represent these numbers on a computer. There they are there. They're represented on a computer. It's not as if a computer can't represent 0.333. So I get a little, the reason I get a little uptight with the word digital is because the area that I used to research is in signal processing, and they talk about digital signal processing. And the thing is, it's not there, the word digital is something else. There, the word digital means sample. Right? You're sampling at a particular frequency. 4.1 kilohertz is what CDs use, or 192 kilohertz, some MP3s running. So just be a little careful and figure out what digital means. Here, digital just means ones and zeros. Right? Here's the example. And that's where it comes from, digits. Okay. And I have spent far too much time talking about, that was section 1.1. I thought it was important to talk about. I normally take a break after about an hour. We've been going for about an hour modulo the startup time of my computer. So does anybody have any questions so far about, this is chapter 1 because I probably won't get too much further into, I won't get to chapter 2 yet. So I do want to talk about it. I'll do that next. I'll continue with chapter 1 after the break, but let's have a 10-minute break, and then we can continue. So if you're interested in all, this is the device I've got. It's really quite cute. Does a nice little, it's got a little amp and voltmeter on it, so you can see what's happening. Even without the resurrection of dead devices, I like being able to see what current my devices are pulling and they're charging, because I can tell, A, I can tell whether they're charging, and B, it shows me how much they're charging.
Oh, it's cold. There's nobody like everywhere.
That's a perfect place to do it.
I still don't think I can do it.
Okay, so let's get going again. I'm not going to spend as much time going through the remainder here. I do want to quickly flip through chapter 1. So I think this is interesting because of the idea of a propagation delay, right? Remember with the glitches assignment, with that 4-bit adder subtractor, we had delays as being the issue. And here's just a single gate. It's an OR gate, right? It's implementing this truth table. And you can see that there's at least two layers, right, between the inputs A and B and the output Y. And that's, again, 2 layers gives, there's a bit of a delay between each one. So that's where that propagation delay is coming from. Okay, and this is just going to go through the truth table and show which is which. Alright? How we get one or the other values. So again, it just gets back to the thing that you can't completely divorce physics from what's happening in the devices. It's always going to get you. I think we know about NOT gates and AND gates and OR gates. I don't think I need to necessarily go through all of those. Right, so that's all good. So then Boolean Algebra. So they did mention it, right? So the whole thing we're doing with ones and zeros was started by a mathematician called George Boole. And that's why the name was started as capital B, Boolean Algebra, right? Because it is named after a person. That's why you should talk about capital G Gaussian noise, right? Because Gauss came up with the idea. And it's a bit, normally if you have the Ian ending, it's usually IAN, right? But here it's, because Boole had an E on the end, we've got to go with a slightly different spelling. I think this is a really dangerous thing to say, as we saw on my first slide with the trick or treat, right? There's not necessarily a one-to-one between the language we use to describe something and the logic expressions we have. There's sometimes a bit of a disconnect there. I think Doesn't mean you don't try, but it just means you be careful with your connection between language and the Boolean algebra. And evaluations, more evaluations. Yes, so there's lots of different ways to write Boolean expressions. Sometimes people use up caret, down caret, and don't know what to call that little right angle thing is, instead of the things we're used to, where we use a plus sign for or and potentially nothing for and, or maybe an ampersand for and. Whether there's much there that I want to talk about. Right, so there's lots of different ways we can write Boolean expressions. We can write them in language. We can write them as an algebraic expression. We can put them in a truth table. We can put them in a Carnot map, a K-map. Right? So just be aware that all of these things are available and they're all equivalent, but they show us different things, or they're useful for different things. There's the simulator. So I taught the introductory networking course a year or so ago now, CET 179, and one of the apparently most difficult things for a lot of those students to get their heads around was a timing diagram. And you've seen it. You've produced the timing diagrams in Model Sim Altera, right? You've produced them, sort of produced them in Multisim. But all it's doing is it's showing a graph of the signals in our circuit and whether they're 1 or 0. So, and regardless of what the circuit is, that's what it's for. That's all right. I think that's all right. And that's just connecting the algebraic expression A or B and C D bar, or D complement. Right, so there's our D complement. There's CD going into an AND gate, and there's A or B. Also going into the AND gate. Same information, just represented different. So I like this example in that it relates to a real thing, airbag deployment, which is very important from a safety perspective. I don't necessarily like it because it hides it hides a bit, right? It's connecting sensors and switches straight into digital logic. And as we've talked about, mechanical switches and mechanical sensors tend to bounce. They're not exactly 1 or exactly 0 during their transition phase. They tend to switch between the two. So, like I said, this is important, but another thing to bear in mind is the reality that there's going to be some sort of debounce happening between any sensor or any switch and the digital logic that we're implementing. So when you have a Boolean algebra expression, that is normally just what's called combinational logic. It doesn't depend on the past at all. It just looks at the inputs and calculates the outputs straight away. The other sort of logic, the other sort of circuit that we've worked with is sequential circuits. Right? The counters I want you to try and get done in Lab 7 are a sequential circuit. And they also depend on the inputs, but they also depend on the past state of the device. Right? So state gets to be important. That's all right. I think we know about drawing conventions mostly. Yep. That's okay. So, Boolean algebra is just another version of mathematics, right? Shouldn't be too different from what you're used to, except that in Boolean algebra, 1 plus 1 equals 1, right? So there are some differences, but there are some similarities. The distributive rule works, right? You distribute A over B or C, A and B, or A and C. There's the complement rule. If you OR A with its complement, then the answer is always 1, because one of them has to be 1. And the identity, right? If you AND anything with 1, then you get the anything. And there's more properties. Right, so commutative, it doesn't matter which order you do things in. For AND operations, A and B is the same as B and A. Same with OR. A or B gives the same result as B or A. If you OR anything with 1, it's always 1. And then there's this word idempotent, right? Which is basically saying it doesn't change. So A or A is A, and A and A is A. My wife is a mathematician. She's a group theorist, and she just loves all that stuff. I like to know about it, but I prefer things to be a bit more practical. And that's all alright. So one of the nice things about Carnot maps, which we haven't seen yet, I don't think that's until chapter 2 from memory, is that we can do less Boolean algebra by hand, right? It's still worthwhile knowing how to do it, right? Distributive law, commutative law, associative law, complements, identities, null elements, the idempotent, involution, and the one I particularly like is De Morgan's law. Right? So De Morgan's law allows you to change an AND operation to an OR operation. Right? You swap over AND and OR. So I suggest you remember De Morgan's law, right? A and B complement is equal to A complement or B complement. Can be important. And I think that's all there. Sum of products. Okay. So we're talking about AND and OR as the main operations. And there's two ways to represent a full Boolean function. One of them is sum of products, the other one is product of sums. Right? Usually we prefer to go with sum of products. So that is a series of variables ANDed together, or another series of variables ANDed together. Product of sums is the other way around. You've got a series of variables ORed together, ANDed with another series of variables ORed together. But Carnot maps tend to go with the sum of product. Right, and the nice thing about sum of product then is you can just have each of the products generated with an AND gate, and all of that fed into an OR gate. Product of sums is the other way around. You just feed all the inputs into OR gates and then AND all of those together. Okay. Sum of minterms. What's a minterm? Michael, what's a minterm? Michael, Frederick this time, what's a minterm?
At the time of doing the assignment, I knew exactly what a minterm was. At this present moment, no idea.
No idea? Eric?
Is it a combination of the variables where the output is high?
Doesn't necessarily have to be high, I don't think. Let's have a look. Right, there's what the textbook says, right? A min term is a product term having exactly one literal for every function variable. So if you've got 4 inputs, A, B, C, D, then a min term is just one of them that has, for example, A, B, C, D, or A, B bar, C, D bar is another min term. It's got one and only one version of every input in the product term. Okay. So for a 4 input logic circuit, you're going to have a total of 16 min terms possible. Right? 1 and 0 for each one, or the A version or the not A version for every one, and so that gives you a total of 16. So if we just have a truth table with all the inputs and the 1s and 0s as the output, a way to write the Boolean expression for that truth table is to just say, okay, if 0, 0, 0, 0 is a 1, then I make A bar, B bar, C bar, D bar as one of the min terms. And for every line in the truth table with a 1, then I get a separate thing. That does nothing to simplify the expression. It can get very complicated, but that is a way to go from the truth table to a Boolean algebra expression. Sorry, I should put that off. So because those min terms are just whether the variable is itself or its complement, they tend to refer to min terms by number. So that in this case the 3 variable ABC, A bar, B bar, C bar is just M0, right? Because you've got 0, 0, 0, here you've got 1, 0, 1, so that's M5, and then you've also got ABC, so that's 1, 1, 1, and that's M7. Right, and another way that can be written, it's split over the page there, is just the sum, that capital sigma sign, 0, 5, and 7. Okay. And I think we know how to count. Let's just quickly scroll through that. See how that goes. That's all right. Yeah, I think that's okay. We've talked about truth tables, so I don't know whether there's much to say about them. Let's see what the textbook says. Right, so all of those min terms are just listed, M0, M1. Usually it's 0, 0, 0 or 0, 0, 1 for M1 in the table, and then the output that the function is providing. Right, here's an example of a 3-variable truth table with only 2 ones in it. So it's going to have the 2 min terms, A bar B C and A B C bar in it. That's all okay. Right, so this is just going the other way. If you've got the algebraic expression in terms of the min terms, you can just take each of those terms and put a 1 in the appropriate row of the truth table. It gets much harder if the Boolean expression is simplified, right? Then one term, no longer a min term, one term in the Boolean expression may put more than one in the truth table. Right, and now this is just talking about what I said earlier about the product of sums, so that's okay. So here's a term that doesn't get used very much, a max term. Okay? A max term is a sum term that has all the function variables exactly once in either true or complemented form. A product of max terms form is a canonical form of a Boolean equation where the right side expression is a product of sum, with each sum consisting only of max terms. Right, so you can see the relationship with the sum of product, right? Sum of product has min terms, so all of the variables or their complements, but only one of them, ANDed together. A max term is, again, all of the variables, input variables, or their complement, but only one, ORed together is a max term. Right, so here's the way to think about max terms. Here we've got, and we're mainly interested now in the zeros of the table rather than the ones of the table. It's kind of funky. And let's see about converting from product of sum to sum of product. Right, so there's a product of sum term. So first of all, they distribute. And figure out all the zeros. And then you're left with the sum of product. Right, so you can't convert between one and the other. So I disagree with this approach. I think I've tried to get across my approach is a 3-step approach: plan, do, review. Right? And they just plan and do, they don't review. But it's still worthwhile enumerating what you do. Right? The first capture is the plan part. How do you describe what you're trying to do with the circuit? The next piece is the do. Do the design. Take the information that you gathered in the first step and then make it happen in a circuit. I would add that from an engineering process viewpoint, you do need to have that review or that quality test at the end to make sure that it works. And then there's just examples, I think. And why study digital design? So there's all sorts of good reasons. I think the main reason is because I think it's fun. But the main reason is because it's on your program. Which is maybe not a good reason. And that's just showing that you can do stuff that's more complicated, right? Particularly the 7-segment display, that's going to be something we need to deal with. I'm thinking for the CPU project that we may want to put out the program counter on the 7-segment display so we can see it. I think that might be fun. And that's it for chapter 1. I'm going to leave chapter 2 until next week. I do want to try and get through all of them between now and the end of the semester. But I think it's worthwhile going through this really basic stuff. The nomenclature, just to try and get that stuff up here. Min term, max term. Understanding what's happening at the basic level, at the physical level, the physics level. That it's, even though we're talking ones and zeros, it's important to know that that's still there, right? But we still need to do it. Okay. Something up here. Now I need to go back to my notes. We did that. We'll push that to next week. I didn't think I'd go off on quite so many tangents, but that's okay. And we're going to avoid Lab 8. Let's just go back and talk about Lab 7, which I think I had from last week. There we go, that's the bounce switch. Where did Lab 7 get to? There we go. Right, so just to remember, we're going to have a clock, again, plan. You need to talk about what the design is supposed to do. Write your VHDL code. Review. Write a test bench. And I want you to show me, or at least write in your write-up, that it actually does test every possible count of the counter, both in the up direction and the down direction, and maybe with a little jig between up and down as well, right? Because sometimes those abrupt changes. This one doesn't do it, but I think a lot of you have found stuff there. The key though is to make sure that you've got the connectivity. I do want the device to follow what is on Blackboard,
Right, let's get the blackboard up. Maybe? I keep forgetting to check the don't ask for 14 days on this one. So. Okay. Yada yada yada. There we go. Courses. No? There we go. 466. Labs. So there is the entity state, right? Now there's a couple of things that you should think about, right? We're going to do an up-down counter. And that's going to be its own separate file. We also have to, I want you to demonstrate it on the board, right? And to demonstrate it on the board, you're going to have to do some debouncing. So you're going to have to do a debouncer so that you can connect up the switches on the board to the clock or the up-down input on the device. And that means you probably need your top level design entity, your top level entity is something completely else, right? Because you're probably going to need two of these, one for the manual clock and one for the up-down. Okay. The other thing is, if you're going to connect up the 50 megahertz clock, I think the lab asks to, right, to divide it down to 10 hertz. So another VHDL file you're going to have to possibly write is a clock divider. Okay, so there's a few things there, and then of course the other thing that you need is the test bench, and that's the VHT file.